All right, how's it going? Good morning, everybody. Alrighty, so let's start. Let's see if you have any questions. Sorry, I had a full office this morning with lots of good questions, lots of good progress on PA2. So we can continue that here if anybody has anything they're stuck on or not sure about on the assignment or hash maps or putting classes together. Can we go over pseudocode for the cleanupWord method? Absolutely. Why is add reference called add reference? The thing we call a teapot is not a teapot. That is why it is called a teapot. That kind of thing. Add reference is the... So I don't know. I think of this as recording all the references to a particular word. If we thought of, a word being in a file as a reference to it. Maybe it should be add index entry or something, but it records, the word and the location where it is in the file. So, but may not be a ideal choice of name. Probably add index reference would have been more clear. Yeah, let's go over cleanupWord. So we're going to take some input string and clean it up and return the cleaned value as the methods return. So there's two ways to think about this. One way is let's take this string and get rid of everything that's not a letter. The dual way to think about that is let's start with an empty string and add to this string everything that is a letter, right? Adding is sometimes simpler than taking away, particularly with strings, because if you take something away from the middle of a string, you've got to, somehow squeeze the two ends together to fill in that space. Whereas adding to an output string is just appending to the end, and that works really well in most languages. So my suggestion was, for each character in your input string, if it's a letter, add to the end of out. And then just return that output string. So how do we do this? Depends what language we're working in, right? For Java, for integer I equals 0, I less than. If this is a string, in.length parentheses will tell you the number of characters in there, I++, and then this is this business that we went through yesterday of in, which is your word, dot, character, at, parentheses, I, will give you the ith character, and you can use that as an argument to this method defined in the character class. So character dot is letter, and you can put a character in there, and this returns a true or a false. So you can use that, and when you can append it to out, and then either turn it into an uppercase when you append it, or if out is a string, you can return out dot to uppercase. And that gives you an uppercase version of the word. How do we call the cleanup method if it isn't static? You don't need it to be static. So, right? I mean, here's a method called multiply, and we can call it by just saying multiply. Here's a method called area, and we can just call it by saying area. There's absolutely no reason or need to make a method static if you're going to call it. The only time you need to make a method static is if you're defining it inside. If you're calling it from a static method, then it has to be static. But if you're calling this from no, we don't call cleanup in main. Cleanup is being called by code inside your probably process file method. And let's pull up the assignment. Right, so cleanupWord is a private method, so you cannot even get to it from main. Is there any chance that you... So what method are you calling it from? You're calling it from process file? Did you declare process file to be static? Okay, tell you what, if you can stick around a couple of minutes after class, let's stay on Zoom and you can show me your code. Or is your code pushed into GitLab? Let me eyeball it really quickly. Nope, I'm on the Linux server right now. So I can compile your indexer, and I get some compile errors, but nothing complaining about statics. So yeah, stick around in Zoom right after class, and we can see what you're doing. So uppercase is part of the string class. So look in the string documentation, and it's 2 uppercase with an uppercase U and an uppercase C. So like that. And that's an instance method, so it's applied to whatever string you use when you say, you know, object.toUppercase. Yeah, right. C is just 2 upper. I think that's all lowercase in C. That's from ctypes.h. All right, awesome. So let's, well, I got all kinds of windows going on here. So let's dig a little deeper into these try-catch blocks. We worked out, you know, a basic example of this yesterday. Where you have a statement that might throw an exception, so you put a try curly bracket right before it, close curly bracket after it, and if it succeeds, everything just runs as usual. But if an exception occurs, it goes into a catch block. And we can actually set this up with multiple catch blocks. So we can say try curly bracket some statement catch, and we can list some type of exception, and put some things to happen. If this type of exception was thrown, we can list another catch block with some statements, and if this type of exception occurred, it will execute these statements. And we can do this for however many different types of exceptions we want. And the first catch block that matches the type of exception that occurred or is a more general type of exception, that's the one that will fire. And so we can do kind of a catch-all by saying catch, exception. And this is the most general of all exceptions. It just says something went wrong. But there's more specific versions like array out of bounds exception, IO error exception, and so on and so forth. So you name those in here based on what type of exception it is that you're worried about, which will typically be one of these. So bad binary operator value exception or bad location exception and so on. And then there's also a finally statement. And you can put statements in here which will execute whether the statement succeeds or one of these catch blocks fires. So that whatever happens, you can always say, okay, at the end of all of that business, I also want to do these things. Now, catch-all doesn't happen to be a real thing, but maybe you could define all to be a null symbol or something. So yeah, just name the exception. So, array out of bounds exception, some variable name, some object name. So let's put some code together to play with this. So we'll do an exception test. All right, so I'm going to play around with an array out of bound exception, a divide by zero exception, things like that. So I'm going to make an array of 5 integers. And I'm going to ask the user to type in a number. And I'm gonna do something really sloppy here, right? I'm not going to, check for has next int or anything like that. I'm just going to open a scanner on system.in, and I'm going to say give me the next integer, right? And I'm going to store that in I, and I'm going to do something even sloppier, right? Now I don't recommend this, but this is a quick and dirty thing that's perfectly legal. Since I'm only planning to do one input in this whole program, I'm just going to not bother saving my scanner in an object. I'm just going to say new scanner system.in .nextInt. Right? And this is legal, but it's a little reckless. Right? If I wanted to input a second thing from system.in, I would have to construct a new scanner and so on. But this will work as a one-liner. So make a scanner from standard in and just give me the next integer that's available. All right, and then let's print out that element of the array. Or let's do this. Let's set data bracket I equal to 100 divided by I. What the heck? And that's going to be our whole method. Yeah, fast and furious. All right, so we've got an array of 5 integers. We're going to get a number from the user, and we're just going to set that element in our data array equal to 100 divided by the number. All right, so why are we doing this? Because that's what we do. So let's compile that. Let's import our scanner. Alright, so I run this enter number from 0 to 2, and it just set element 2 equal to 50. Alright, and if I do element 3, it'll set element 3 equal to 33. Alright, now what happens if I put in, 999, right? It's going to try to set element 999 equal to something, and there is no element 999 in our data array. We get an exception, array index out of bounds exception. Alright, so let's make a catch block for that. So I'm going to put this in a try statement. So I'm going to name the exception, and we usually call it E, but we don't have to. We can call it anything we want. And so I'm going to say, let's print out a message here. I'll say I is out of bounds. And I'll return. Alright, so now if we get an out of bounds error, instead of just having it complain on the screen, it should jump down here to this catch block and print out this nice controlled message saying that the value I is out of bounds. So put in a legal number, nothing happens. Put in an illegal number, and it tells me that number is out of bounds. So we're trapping the exception basically, right? Now, if I put in a number like 0, it's going to try to set element 0 equal to 100 divided by 0. That's an arithmetic exception, division by 0. So that's a different type of exception. And we can try to catch that. So we'll catch this. Yes. Wascally exceptions. All right, so it lets us not only trap exceptions but do them in a more fine-grained way. So everything legal, no problem. Illegal index, we get our out of bounds message. Division by 0, we get our division by 0 message. And we're exiting in this case, but we don't have to exit. We could, do something else appropriately. Whereas if we don't trap these exceptions, we just get this message, and the JVM will force our program to exit. So let me move my try block. Into here. And so here's my error again about symbol not found I, because I was declaring I in this statement, which is inside this try block. Right? Now you can declare it in there, but it's local to that block. So if I want to be able to access it outside, just move the declaration outside the try block. And, I can declare it here also, but this will have nothing to do with this. right? So this is a subtle issue. Oh, nope, it's smart enough to save you from doing that. Okay. All right. So here again, it's telling me this variable might not have been initialized because if I get an exception up here, I might come down to this block and find out that I is out of bounds. All right. So what do we do about this, right? You got to look at your logic, and the compiler is not always able to understand your program as well as you are, right? I is an integer. Okay, I'm going to try to read this in from the user, and that should succeed, right? And I might get an exception here. And if I do, then I might end up down here, or I might end up down here. The compiler doesn't know that, though, right? All it knows is that somewhere in here, including maybe before I assign a value to I might have an exception. And it doesn't know what kind of exception I might occur. It might be that I get an out of bounds exception, and I'm going to try to use the value of I down here. So we can, in this case, kind of band-aid it. And we're really doing this for the benefit of the compiler, right? You and I can look at this and we know that if I does not get a value, we're not going to end up down here. But the compiler doesn't know that, right? We're kind of asking it to solve the halting problem in some sense. So this is a band-aid. It really keeps the compiler happy. So now if we run it, that's all fine. That's in bad bounds. That's a 0. All right. But what I've done is I've moved that that scanner that gets the next int. I've moved that into my try catch block. There's no try in Y, but there is a Y. Now if I do this, if I type in ha ha ha, what happens? I get this Java utility input mismatch exception. And that's coming from scanner. Because I said give me the next integer and there was no next integer. Alright? Now the proper way to deal with this is, don't ask for the next integer until you've said is there a next integer. So first I would check to see, if scanner.hasNextInt, in which case I'd say, I equals scanner.nextInt. But since I'm being, fast and reckless here, right, I've got a potential for another type of exception. So what we're going to do for this is instead of catching that particular exception, we're just going to make a catch-all block. So we're just going to catch exception E. Any exception that's not already caught. And in this case, I'm going to print out the value of that argument error so we can see what the exception is. Yeah, we can call it all. I like that. So now if I put in something and it's not one of those exceptions I defined, it says some other exception occurred, and it tells me the name of the exception. So you can do a lot of really precise, well-managed exception catching and handling in here. But you can also abuse this. You can get really sloppy. Like I say, I've seen people put their entire method inside one big try-catch block so that, if anything goes wrong, I'll just print out a message, right? And sometimes, maybe that's a good thing to do, but usually not. Usually you want some kind of very, very small try block. And, I could put this in a try-catch block. I could put this in a try-catch block, and so on. Yeah. All right, and then there's the mysterious finally block. Yeah. So the structure of the try catch finally is a little bizarre. Um, so we're going to try these statements, and if we get this kind of exception, we'll execute this. If we get this kind of exception, we'll execute this. If we get this kind of exception, we'll say some other exception occurred, and let's go ahead and return after that. And if no exceptions occurred, then we'll go ahead and we'll say goodbye from the main program. GDB does sound kind of strange. And the finally block will say inside the finally block, okay, here's the deal, right? The finally block gets executed after either your try block succeeds or one of these catch blocks fires. And the finally block always gets executed. Okay, so you're going to see something really bizarre in here. I'm going to drag this window outside so we can like fully embrace the weirdness of this. So we'll compile this and we'll go ahead and run it, and if I put in a legal number, it executes the try statement, it executes the finally block, and then it says goodbye from the main program. Alright, if we get an exception, like I put in a negative index, what just happened that's really weird? So we did leave the finally, right? We didn't say goodbye. What were we supposed to do after we said I is out of bounds? We're supposed to return. Print out I is out of bounds and then return. So it printed out I is out of bounds, but before it returned, it printed out we're inside the finally block. Okay, this is a little strange and totally unexpected. So the way try catch blocks work, even if your catch block says let's return, let's get out of here, it's still going to come down and do whatever's in the finally block first. Yeah, so that's definitely a Okay, I've never used this, so I don't know what the use cases are where this makes really good sense. But finally always happens, right? Even if your catch block says return, before that return fires, it'll jump down here and do the finally block. Really good question is what happens if you return from the finally block? And it either returns from here, or it goes back and returns, or the universe collapses. I don't know which. Do it. Give it a try. We have to put this inside a method so we can actually return a value. Well, maybe, yeah, because this is void. But throw it inside a method and return a value and see which happens. But do it in a virtual box so that if the universe collapses, it's not the real universe. No. All right, so that's basically how we do try-catch blocks. So that's it's there if you need it, right? But if you use it very, very specifically, right? Just put this around where you expect an error to occur, and don't fall into the trap of, you know, I'm getting some kind of error, so I'll just put a try-catch block around this. Because exceptions are exceptional, right? They're not expected, which means if they occur, there should be a reason that maybe we need to be, you know, handling proactively. Your machine shop instructor loved the phrase isolated universal extinction event. That's a cool teacher. All right. So shifting gears, let's talk about binary trees, right? We all love binary trees. And let me put this code on the server. All right. So PA3, we're going to be dealing with binary trees. They're not going to be binary search trees. They're going to be what we call decision trees, but they'll be binary in the sense that each node will have 2 children. They'll be full. Every node will have exactly 2 children. And so, you know, the usual pictures we like to draw. And so I want to explore how we implement binary trees in Java. And so we're going to cobble this together ourselves. So we're going to make a class. I'm going to call it, you know, tree. And what kinds of things do we want in our tree class? From the perspective of somebody who's using this, what do we want to do with trees? Oh, quoting the Lorax. So I'll start you off. We want to construct whatever that does. Traverse, add nodes, remove nodes. Sounds good to me. So let's add a node. Let's have a print method for traversing, and we'll just traverse in order. And I'm super lazy. I'm not going to bother with a delete method. We could have a search, and that's probably enough for demonstration purposes. Yeah, remove would be useful, but you know, that's involves writing code, so don't want to do that. All right, so when we code up trees in Java, it's a little bit different from C. Because we're being object oriented, right? We have a tree. If we want to, for example, you know, print out our tree. So let's say print is going to be a method that does left node right traversal. If print was a part of the tree class, right? So let's say this is my tree T. If I say t.print, well, you know, I've got this tree, and inside the class, you know, I've probably got the root node somewhere, so I've got a node that's going to be called root. And we know how to print in left node right. First, we print out root's left subtree, and then we print root's data, and then we print root's right subtree. So we do the usual recursion thing, right? The difference is that root is a node. And so if we say root.left.print, this thing right here is not a tree. It's a node. Well, nodes and trees are the same thing on paper, right? But in implementing this in Java, this is going to be a tree object, right? But this thing, when we go to the root of the tree and we look at the left child, that's going to be a node object. So we're going to end up writing a pair of methods for each method we want. We're going to put a print method in the tree class, but also in the node class. And it's really the node class that's going to do all the recursive work. Okay, so that's just a warning for what might look like some weirdness coming up. So let's do this. All right, so we're going to define a node class eventually, but let's assume we've already got nodes. So we're going to need a root. So there's our root. Let's make a constructor. So and the constructor is just going to set the root to be null. So that's an empty tree. We'll put a print method in. Which will traverse and print and left node right. And here what we're going to do is we're going to basically use the traverse method inside the root node. Alright, so we're going to do root.print. So in the tree class, add, search, delete, print, all of that stuff, those are really just wrappers around calling those methods on the root node. Alright, but we got to be careful here, because the root might be null if the tree is empty. So we'll explicitly check if the root is null, we'll return. Otherwise, call the traverse method in the node. Alright, and add is going to be the same thing. So if the root's null, we'll just return. Otherwise, we'll add the node to the root node, right, the subtree whose root is root, right, which is our original tree. Hey, I know, unforgettable. So, node root. That's the actual root of the tree. So let's think about how we're going to run this thing. Let's write some main code. So we're going to say something like, you know, tree t equals new tree, t.add 12, so we're going to do something like this, right? Construct a tree, add a few nodes to it, and then print out the nodes in order. So when we construct our tree, right, all we're really going to do is set this root node to be null to say there's nothing in the tree, right? And this is the thing that we use to get a hold of the tree. It's our handle to the whole structure. How come you don't have to say new root? Good question. I guess I don't have to because I'm going to set it equal to null. Yeah, I'm declaring root to be a node. When I construct my tree, I'm going to set it equal to be null, right? If I want to actually construct a node, then I'm going to have to say new. And in fact, it's going to default to null anyway. But when we start creating new nodes to tack into our tree, we're going to say, new node. There is no import for trees. We're writing this ourselves. So no imports. All right. So this is our whole tree class, right? It doesn't really do a whole lot, except provide us some wrappers to calling things in the node class. So the node is where all the stuff is going to actually happen. So let's make our node class. So what does the node have? Well, it has a data field, which for us we're just going to do an integer. It has a left child, and it has a right child. Yeah, building from the sky down is kind of like, unless you're talking about like Minecraft or something, that's top-down design. And that's really what we're doing, right? If you start off with this, I just closed my chat window. Right, if you start off with this, you're designing the high level of your program, and then you're working your way down and designing the tree class, and then you're working your way down from there and designing the node class, and so on. So there is top-down design, and that actually works well for object-oriented languages. All right, so let's see. I closed out my camera. That's okay. So a node's going to contain a piece of data, a left child, and a right child. Okay, let's make a constructor. And we'll just take in an integer. And so the constructor will make a node that has a piece of data, right, which has a value of n that we just passed to it here, and then left and right children will be null. So this is how we make a single node. And so let's make our add method. So let's add this node to the tree. All right, so how do we add a node to the tree? We compare it to the root. If it's bigger, we add it to the right subtree. If it's smaller than the root, we add it to the left subtree. So that's pretty easy to code. If n is bigger than data, then right.add n. Otherwise, left.add n. Temporal accords, yeah. So this is a good first order rendering of our add method, but there's a problem with this. So what's the problem in this code? besides the possibility of time travel. Base case, right? If we have a node that has no children, then when we say write.add, write is going to be null. We're going to be calling, the add method on a null object. We'll get a null pointer exception. So that's a problem. So we need to deal with the base case. So if write is null, then what should we do? No write child. So make this new node that we're adding to our tree the write child of the current node. Alright, so if write is null, then we'll set write equal to a new node. Otherwise, we'll call the current write child's add method to add n to our tree. Alright, now we're going way more curly braces than I normally like. Otherwise, we're going to add to the left subtree, and we're going to do the same thing here. If left is null, left equals new node, n, else add it to the left subtree. Alright, does that look reasonable? Yeah, so normally, I don't go this deep with curly braces. I would probably say if write is null, then make a new node and return, and then I would just move this over as, if we didn't return, let's add. But, curly braces are okay. Two curly braces at the top of add. Thank you. Awesome. Good spot. All right, so there's an add method. Let's oh, we got 1.5 minutes. Let's make a print method. So if the root is null, we're going to return. Well, we don't have a root. We're not in a tree. We're in a node. All right. So how do we print? First print the left subtree, then print the root node's data, and then print the right subtree. We're in a print method coming from an object which is the root node, right? So the root always exists, but the left subtree could be null, right? So here's all we got to do. If left is not null, call the left print method. And then we'll say print out our data value. And then if write is not null, call the write print method. All right. I'll be amazed if this actually works. It compiles, that's part of it. It did not print anything. T.add, T.add, T.print. Tree.print, root.print. 48 errors from one curly. That is probably the record. root is null, return root.add. All right, so there's something missing in here somewhere. I don't know where, but anyway, that's the basic setup for trees. We are out of time, so I'll put this code up on the server, and you are welcome to figure out what the problem is. And if you don't figure it out, we'll talk about it next time. So tomorrow we'll do an open lab again. Okay, so come by if you want to work on PA2. Or anything else. I'll be in class, I'll be hanging out, and we can work on code. No lecture tomorrow. Okay, open lab. All right, cool. Have a good one. I will see you next time.